Alright, so in this lesson we're going to look at collisions that happen in two dimensions and really think about what we would do in a three-dimensional collision. Many collisions with objects do happen in two dimensions or three dimensions. If you think about what you have to do to have a one-dimensional collision, you pretty much have to have things that are stuck on a track and are only able to move forward or back. Most collisions happen where things can move forward or back, side to side, north, south, east, west, maybe north, south, east, west, up and down. So we need to think about how do we deal with collisions that happen in multiple directions. Thing to remember is that momentum is a vector, so I can break it up into x and y components, and I can apply conservation of momentum to these collisions by applying it on both the x side and the y side. That the x component of momentum is conserved and the y component of momentum is conserved. So let's look at a problem, and I have problem D6. And this is a ball with a mass of 2 kilograms is moving across the table with a velocity of 3 I hat plus 2 j hat centimeters per second. Strikes a ball with a mass of 4 kilograms initially at rest, and after the collision, the 2 kilogram ball is moving at a velocity of I hat minus 4 j hat centimeters per second. What we want to do is write the velocity of the 4 kilogram ball after the collision in unit vector notation. So here we go. M1, M2, V initial 1, V final 1, and V initial 2. If I say initial momentum equals final momentum, I can say M1 V initial 1 plus M2 V initial 2 is equal to M1 V final 1 plus M2 V final 2. And it's really V final 2 that I'm looking for. Since V initial 2 is 0, M1 V initial 1 is equal to M1 V final 1 plus M2 V final 2. If I'm solving for V final 2, I probably want to subtract M1 V final 1. I can then factor out the M1 and then divide by M2. So you get the ratio M1 over M2, V initial 1 minus V final 1 is equal to V final 2. So let's work this out. Plug in my masses, plug in V initial 1 and V final 1, and really the nice thing about unit vector notation, if you remember right, is I can combine my terms. 3 minus 1 is 2 I hat. 2 minus a negative 4 is plus 6 j hat. 2 over 4 is a half. So what I end up with is V final 2 is I hat plus 3 j hat centimeters per second. Now if we wanted to figure out is this a collision where, say, kinetic energy is conserved, we need to do a little bit more work in order to do that. We could maybe play around with these numbers. It looks like at first glance that this is probably one of those collisions where kinetic energy is gained somehow. We don't know enough about these balls to know maybe they're like super bouncy balls or something. We don't know. So the second one that I have is I have a disk of mass m moving to the right at a speed of v0, and it collides with a disk of mass 2m initially at rest. So here's what we have initially. After the collision, both of the disks are moving at different velocities. I'm going to call them v1 and v2, but they're moving in a direction that's an angle of theta away from the initial direction of the original moving disk. So these angles are the same. What I want to do is find the speeds of both disks after the collision. So figure out v1 and v2. So what I'm going to do is separate it in the x direction and the y direction and say p initial x equals p final x and p initial y equals p final y. Well, in the x direction, my initial velocity is m v initial. My final is m v1 cosine of theta plus 2m v2 cosine of theta. And the reason why it's cosine of theta is we're really looking at this direction. Now in the y direction, my initial momentum is 0, but I have m v1 sine of theta minus 2m v2 sine of theta. And the reason why this is minus 2m v2 sine of theta is 2m is moving down and m is moving up. So I have a system of two equations with two unknowns, v1 and v2. Let's solve them out. First thing I'm going to do is cancel out some like terms, and every one of these equations I can divide by m. On the y1, I can also divide by sine of theta. So I could say v initial is equal to v1 cosine of theta plus v2, 2v2 cosine of theta. Over here I can say 0 is equal to v1 minus 2v2. Now this works because the angles are both the same, and one of them is twice the mass of the other one. So it looks like this one here I can solve for v1, that 2v2 equals v1. And so what I can do is I could say, well, 2v2, that's equal to v1, substitute that in, And so I can figure out what V1 is. It looks like 2V1 cosine of theta is equal to V initial. So it looks like I could say V1 is equal to V initial divided by 2 cosine of theta. So V1 is going to be dependent on how big the cosine of theta is. It looks like the closer to horizontal, well, let's think about that. Yeah, it looks like the closer to horizontal this thing gets, the larger V1 gets with respect to V initial. Kind of an odd result. If we do the same thing here and say 2V2 equals V initial divided by 2 equals V1, which is V initial times 2 cosine of theta, we get V2 is equal to V initial divided by 4 cosine of theta. What this really suggests is that if theta is equal to 0 degrees, this is a pretty easy problem to actually work out. And I can actually figure out what the two velocities of the two balls are. If theta is equal to 90 degrees, well, that can't happen is basically what this is saying. So that's your answer. How does V1 and V2 compare to these angles? So that's kind of a quick overview of a couple of questions dealing with two-dimensional collisions. If you did a three-dimensional collision, you would just say momentum is conserved in the x, momentum is conserved in the y, momentum is conserved in the z, and you'd be done.